Hey, how's it going, guys? My name is Russell, and today I'm sure, as you know, I'll be speaking about functional programming. I work at a company called Big Brave, and I worked as a React developer. I focus on writing code that's communicable and understandable, and I hope to introduce you to some of the ways in which functional programming allows that. But outside of that, I find myself spending a lot of time playing sports and learning, and more specifically, any sort of field that's related to consciousness. In other words, anything that better illuminates my experience is kind of what I gravitate towards. And today I hope to introduce you to my worldview and how I believe functional programming is an optimization for the shortcomings of the human mind with regards to writing good code that's communicable with ourselves, understandable to ourselves, as well as those around us. So to begin, I want to start with a very peculiar phenomenon that we often take for granted, I think. It's experience itself. It's how do we come about constructing the world around us? You see, if we drill deep into two elements, as an example of how this process works, we find the first character to be the brain, this 3 pounds of jelly-like substance lodged within a skull, blind to the world besides for the inputs it receives from the senses. Now, if we look at one of those as a case study, the eyes, and we see that they pick up such a small fraction of the potential possibilities that are out there, it raises the question of how much we're selectively filtering out, how much we're not paying attention to. And the reason it matters, if you haven't caught on, is that our jobs require us to pay a lot of attention to things. Our jobs require us to retain a lot of data and information. But if we look at the way we're designed, we're not actually optimized for this. So I'd like to do an examination of that today. Now, the reason we ignore so many details is that we are optimized for very specialized functions. I'd like to make an analogy to a cell in your body. If we were to look at a hemoglobin cell, it's highly specialized at transporting oxygen throughout our body, and it need not be aware. In fact, it can't be aware of the other processes and functions that surround it in order to be optimally efficient at what it does. Now, in speaking about programming, I'd be remiss if I didn't take this opportunity to highlight the compositional nature of life. You see, if we look at these hemoglobin cells and their combined efforts, they result in higher order and higher level functions and processes. And the compositional results of those processes result in even higher levels. And this goes all the way up and down the levels of understanding. Now, the level we're looking at is the human level. And with regards to a specialized function, we've got to understand that we are designed to propagate our genes. That's what we're efficiently evolved to do. Now, the cost of this is that we selectively tune out a lot of information and a lot of data. And like I said, this is important because as programmers, our job is to tune into and be very aware and attentive of a lot of data. So we begin understanding this and we begin examining where our shortcomings lie in order to optimize for these things. When analyzing things, we tend to look at their properties, and the property to analyze humans that I want to focus on is the property of behavior. We define it as an environmental adaptation that's purposeful and goal directed. Another interesting facet of this is that as we adapt, we become more efficient, meaning we need fewer resources to accomplish the task, to achieve the objective of our purpose. Now, this is important to note because we're optimized for environments that are very different from the ones we now inhabit. To explain what I mean, we need to place this in a bit of historical a background. So we start the time of 3.8 billion years ago with the emergence of the universe with the Big Bang. But it's up until 300,000 years ago, if we fast forward a bit, that our story starts to get interesting because we find ourselves at the advent of the generation of Homo sapiens. And this is an important milestone because these people are genetically identical to us. If you were to take a child from 300,000 years ago and raise them today, they would be indistinguishable from a child born in our own day and age. But we need to go even closer back to be able to understand this, and especially to be able to understand who we are as a result of the behavioral adaptations that we developed. So for 300,000 years, we were primarily hunters and foragers. The very reason you can see color is to detect ripe fruit. That is a behavioral adaptation to the environment. Now, things started to change drastically 12,000 years ago as we adopted a new environment. We created a new environment, in fact, that required us to work longer and engage in different activities. But even this isn't significant for the world that we find ourselves in today, for we're immersed in a complex society with abstraction built upon abstraction that requires so much of us. And in much the same way, that the farming and the environment that was created as a result of it require different behavioral adaptations to the hunter and forager of yesteryear. 5,000 years ago, we find ourselves being introduced to complex abstractions, but only a small subset of society was actually exposed to this. So for a more realistic picture, we turn to 100,000 years ago, where maths becomes a major profession, where people are spending their time behind desks, not behind machines, where people find themselves behind desks using their mind, not out in the fields looking for berries. Now, the reason we choose maths is because conceptually it's very similar to programming. And as we progress further in this talk, you can see how by more closely aligning that worldview, we can produce better code as a result. So maths is a logical abstract representation of physical properties. We selectively tune into things and tune out of other things in order to be able to compute them in computationally limited systems. Not only that, but by having a set, a standard, a framework of shared understanding, we can now better reason about and communicate with each other as we're dealing with the same ideas and constructs. This allows us to manipulate them and build on top of them. And this is the world in which coding occurs. Now, let's look at that time scale again, and let's actually crunch some numbers. And remember, we're looking at 5,000 years, which isn't accurate. The more realistic representation would be 100 years ago, but this should still drive home the point. So for 1%, 1.6% of human existence, we've been exposed to a world of complex abstractions. So let's have a look at that. For 98% of our existence, we spent our time primarily hunting for animals, foraging for food, and engaging in physically taxing activities. Contrast that to today, the component that makes up 1.6% of our existence, we're involved in complex abstractions and mentally taxing activities. A way that this may seem a bit easier to comprehend is imagine if for 98% of your existence you ate fast, fatty foods and performed little to no exercise. For 1.6 of the most recent of your historical account, you ate healthily and you engaged in a lot of exercise. I don't think you'd be surprised if you were not behaviorally and biologically adapted to being a healthy human. Now, this is a useful analogy as it takes a large time scale and time frame that we aren't good at comprehending, and it draws it into the here and now. But it's not entirely accurate, because whilst we can see the world we've come from and what we've adapted towards, progress, especially for humans, isn't linear, because we have the ability to reflect on our behavior and modify it in a way that has allowed for such rapid advancements that we can be thankful for the technological wonders we have today. Now, I want to provide a framework for understanding experience. Firstly, when encountering any situation, we observe it. We watch ourselves and others by performing experiments, reading a book, or studying history. We then need to internally represent what we just observed. We've got to have a way and a framework to be able to work with and reason about the observation. We can then take our previous models and mix them together and combine them to create novel information, to expose knowledge and wisdom. And eventually we take those new models that were created from the act of manipulation and we act upon them. And this feeds back into the observation as we see what we do. And this cycle repeats itself a lot. And I set it out because we need to address each of these points. So let's do a quick recap of where we are and where we hope to go. We've viewed the environment that we're adapted for, and we know that this is useful to explain why we are the way we are. What I next want to answer is, what do I mean by the way we are? What is our design? What is our nature? What are we good at? And what about the way we are is relevant to programming? And more importantly, what about functional programming caters and overcomes this obstacle? So to start this journey, we need to attend to attention itself, and we enter a world of invisible gorillas, magical numbers, and I hope you will enjoy the ride that we're about to embark upon. So we start with attention, like I said. Attention being the process by which we selectively attend to relevant bits of information and selectively discard that which we deem unnecessary for the process of computation. I'm sure you've all had the experience of being on both sides of the story, either reading a book and being able to drown out the world around you, or attempting to read a book and being inundated and overwhelmed by the auditory sensation of the environment you find yourself within. Now, this is operating on the level of perception, just like the example of our eyes picking up a small subset of all possible electromagnetic waves. What you perceive is a sliver of what's objectively out there. If you are familiar with the blind spot test, you'll know what I mean. In this experiment, a dot and a cross are drawn on a piece of paper, one of your eyes is closed, and you are asked to move this paper at varying lengths until the cross disappears. This results from the fact that where our optical nerve joins at the back of our eye, there is a small gap where no retina can sit, meaning that there is a gap in our visual field. But we do not perceive this, for our mind constructs a unitary experience. Something that drills this point home even more is in 1999, I feel like there's way too many nines there, but an experiment performed by two Harvard psychologists illuminated this quite nicely. They had a video of two teams playing basketball, one in white, one in black. Your job as the participant was to count the number of passes between the team in black. Now, this wasn't as easy as it sounds, as the people were shuffling themselves about and intermingling, and it could require a certain level of cognitive effort to be able to accurately do this. But it turns out most of the people did just that and got the correct answer. But over 50% of them actually failed in the real and true test of the experiment. You see, halfway through the video, a man walked into the center of the stage dressed as a gorilla, banged his chest, and proceeded to exit to the right. They dubbed this term inattentional blindness, and it falls under the broader category of cognitive bias. A study known as behavioral economics has emerged as a result of studies just like this, and they found countless other examples. You may be familiar with some of the ones you can see on the screen, but the essence of it is that we figured out that humans aren't rational. In fact, we're predictably irrational. But as with the theme of this talk, predictability lends itself to predictability, to determinism. And with that, we are able to overcome our shortcomings. The invisible gorilla experiment was performed in 1999, but well before that, we were starting to become aware of our own shortcomings, especially in the world of attention. In 1956, a psychologist by the name of George Miller introduced an experiment titled the magical number 7. What he was looking at was our working memory's capability. This is our short-term memory, much like our RAM. It's the thing you use to hold on to bits of information. It's the thing that's engaged when you're programming and trying to keep track of variables and trying to keep track of functions and the things that you can immediately access in front of you. It was such common knowledge that was baked into the length of a phone number. The reason that this is important is because it means that we are bad at parsing code mentally, as that is using our working memory. We're bad at immediately grasping abstractions because that requires us to hold many different mental models in our head at the same time. And if we only have 7 bits of memory available for us to do that, you can very quickly see the bottleneck in the system. But luckily, we can hand this task off to our computers. And this trend shows itself in the fact that we no longer commonly use, or the majority doesn't use, low-level languages like machine code or assembly. But for some reason, we don't take this all the way and embrace it fully enough in the style and structure of our code. Now, this is where functional programming fits in. It's often introduced as abstraction and composition, and that is true, and I wish to go into detail on that. I want to introduce the idea as a specification for healthy coding habits. I want to introduce the idea as a set of rules that complement our own shortcomings and optimize for our strengths. Remember the analogy I used earlier of a healthy diet and an unhealthy diet? Well, I want you to think of functional programming as a very healthy and restrictive diet. If you lived in a town that only sold healthy foods, you may be upset at first because it may be difficult to adapt to that, but once you had adapted to it, you would be a lot healthier as a result. Now, we all know that things can be done well or poorly, and dependent on the limitations and the rules that a system has set up, often determines how well something is done. Now, what I'm about to show you and the things that I'm sharing in my talk, they're not a silver bullet, they're not the ultimate solution, but I believe that functional programming is conducive to the way that we think, and it is that healthy restriction and limitation that can engage us in practices that produce the best results. But the main idea is that I want you to be taking a more thoughtful approach, and I'm offering you a framework and a tool set with which to do so. So I promised that we'd get to abstraction and composition, and I thought a nice way to do that whilst introducing functional programming is to give you a little demo of lambda calculus, because that really is the roots and is the heart of a lot of what we perform today. So let's dive straight in. So what I hope to show you now, or rather demonstrate, is an introduction to lambda calculus using JavaScript. So we've got to understand that lambda calculus was invented in the mid-1930s. I'm not too sure of the exact date, but it was developed as a mathematical attempt to formalize computation. So think about that. This whole language had to be able to be defined in terms of a pen and paper. And as such, it doesn't have the capabilities that our programs do have, such as being able to reach outside of a function to be able to access some sort of state. You wouldn't be able to do that if you've just got a pen and a piece of paper. In fact, if you've got a pen and a piece of paper, functions become very limited. You see this function over here. What I've done is I've given it a label so I, as a human, can understand it. I've then given it inputs, and I've given it an output. Functions don't get any more complex than that, except a function can have the function body of another function. So we've got a label, we've got an input, and we've got an output. Notice how the function body can't go and reach outside of itself and do anything. So if we were to build on top of this, I could create a function that would take its input and it would return a function that I've previously defined. So let's correct this and get that back. So conceptually, what this function does is it takes a value and it returns a function that looks something like this. So if we were to write it in terms that humans could understand, we could say that this function takes a first element, a second element, and it returns the first element. So this function is selecting the first item. We label it like this so we can understand. And this is what we should be doing in our code. But often we are wasting those 7 bits of information with unnecessary details. I'd like to drill home the simple idea that code should be organized. And it should be well documented and it should be well labeled. And we'll expand upon this, as this should be common knowledge. Now, I said that this was a formalized attempt to explain computation, or rather to formalize computation in terms of mathematics. And if we know programming and we'd want to know where we'd start with our primitives, our lowest level elements. And for us, that would be a true and a false element. So what we're dealing with is the category of bools. So the category of bools can be defined as a set of two items, and for our sake, we will call the elements of that set true and false. But again, these are just labels, and we could call them whatever we want. Now, an instance of bool would be one or the other. An instance of bool would be true or false, but never both. So if we're to implement this in a language where all we have are arguments in our functions and the returned value from those arguments, it seems difficult at first, but the limitation actually guides the implementation. So if we take our true and false from up here and we want to implement these as functions, we think about the properties. So true is an instance of bool, and bool has two elements. So it takes a first element, it takes a second element, and it returns either the first or the second. So we'll arbitrarily choose the fact that it's returned the first. False will be quite similar. It too is an instance of bool, and it will have the same signature as it needs to deal with the same elements. So it takes a first and a second, and seeing that true returns the first, well, that means that our instance of false will return the second. Now, conceptually, this is what true and false is if we represent it in a functional manner, but it's not very useful for us because we can't actually see how this would be applied. And in order to do that, we need to add to our programming language. We need branching logic, a conditional, which we will find in the case of an if statement. But remember, this is purely functional and purely maths, and we don't have the if construct. We don't have the format of these different branches to utilize just yet, so we're going to have to implement these ourselves. So in this instance, we will log out the fact that I'm true. Otherwise, we log out the fact that I'm false. And that's what our if looks like. So if we were to run this, we find that I'm true. And if we were to change that, we find that I'm false. Like so. So let's try and mimic this. Remember, when we implemented true and false, we were limited by the construct of the language, and that guided the implementation. So if I create a function that represents if, the first argument that I would receive is a Boolean. So if takes a bool. The second argument it receives is what it does in the first branch. And what it does in the else condition is the second branch of our decision tree. So let's place this here so we can see what's going on. So we will get the action to perform in our first branch and the action to perform for our second branch. And immediately something interesting happens. You see, the signature of this function is just a higher order function. So if we have a first and a second and we've got a bool, we can call our bool, which luckily accepts a first and a second. And in theory, we should have branching logic. So to test this out, we can now cheat a little bit because we're not going to implement strings and numbers just yet. But here we are first, and here we are second. So if I break the rules and save that to a variable, and log out the results, we should see that I'm false for our if condition in the imperative way using the primitives JavaScript provides. It leads to the second condition, which is what we expected. And our if being true should lead to the first, which is what we see. So let's test this out for false to make sure that it is working as it should. And I'm false and I'm second. Just for fun, let's add one more onto this and say, what if I need to negate my bool? So again, if we're limited by arguments and the values that they return, we firstly get a Boolean. Then what we're doing is we're building on top of our previous abstractions. We're using our functions and composing behavior, starting at the lowest level and building our way up to more solid abstractions based off things we can trust. So if, and now we can take our bool, F our bool, and we want to flip it around, because remember, bool is selecting a first and a second. So if I am true, so if in this instance I'm true, I would like to receive a false back. Otherwise, I would like to receive my true. And this is much like a ternary expression. If I'm true, I want to be false. Otherwise, I want to be true. So if we are to test this out, and if I am not false, I would expect to be first or true. And just like that, we have our answer. Now we could go on from here and start to build and into our language and other logical operators. Once we've done so, we can work on representing numbers in a recursive format. You see, by programming functionally and looking at such a low level, it forces us to look at the properties of things and to truly come to terms with the abstractions we create. So we could represent numbers as a recursive execution with the number of executions representing the count that we're keeping tally of. Once you've got numbers, you can map those onto ASCII characters. And soon enough, before you know it, you've got the base level of a functional construct language. And that's what lambda calculus does for us, which is a whole lot of fun. So that was the start of lambda calculus. And it was developed by this man, Alonzo Church. At the time, there were three mathematical formal proposals for computation. The one that we just introduced ourselves to, namely Alonzo Church's lambda calculus. Secondly, a very similar proposal by Reines, which he labeled recursive function theory. And lastly, the most widespread and impactful one known today, Alan Turing's Turing machines. So the difference between these, if we are to group the two functional approaches together and put Turing's on the other side, is that Turing believed in the idea of mechanized symbol manipulation that was time order evaluation dependent. I'm sure you can imagine a punch card system or vacuum tubes that are dependent on the state of previous computations in order to calculate the present position. But the way that the functional approach differs is that it's based off structured function application, and this means it's time order evaluation independent. A nice example of this is string concatenation. If I am to take the string hello my world, I can join hello and my, or my and world, in much the same way in maths that we can add numbers in a certain order. And these are some of the mathematical properties that make it super handy to work with and deal with. But that's not what my speech is about today, so I'll leave that for someone more capable and able than I to discuss that in detail. I showed you in the demo some pretty novel implementations, and from my point of view, it makes complete sense that this illuminates the idea of composition and abstraction, but for someone just watching, it may be a gimmicky effect. But I think that this is, truly indicative of that process of repeated composition, which is what we do all the time. To give a bit more context to this, let's look historically. Computation can be said to have begun with the introduction of Boolean-like logic with the Greeks. This was later formalized by people like Boole and De Morgan, who actually built some sort of propositional calculus around this. But after that, we got introduced to ideas of predicate calculus, which took the bools and added on top of them by allowing us to perform logical operations on non-logical types. Moving forward, mathematicians got a hold of this and saw the power and potential within it to build on top of these solid abstractions. You had the likes of Bertrand Russell producing Principia Mathematica in an attempt to formalize computation. He was halted by Kurt Gödel, who came across the incompleteness theorem, which was later answered by Alan Turing. That led us to the day and age of modern computing and the languages that you know, love, and use. If we were to look at this from a different point of view, we can see that we had propositional calculus. And by observing, modeling, manipulating, and acting upon that, we were able to create more advanced forms of maths and more useful forms of maths. Again, we examined, we modeled, we manipulated, and we acted upon it. And we could create actual computers. Again, we repeated this process and created languages. Again, we repeated it, and soon the languages that we created started to look like the language we use. And immediately the sound of that sentence just sounds correct. Shouldn't the coding language you use mimic the language you generally use? There's the experience that we've all had of interfacing with someone who is not of the same language as us, and that barrier can be quite an impediment to progress. And as with programming and as with life and as with maths, as soon as we see repetition, we can abstract away. And in this instance, what we see the trend is moving from an abstract low level implementation, which is difficult for humans to understand and manipulate, towards a higher level of abstraction, moving towards code that is easier for humans to understand and manipulate. So surely we should be moving in that direction. Well, in order to do that, we need to understand the specific properties of what's being enhanced. So again, on the low end of the spectrum, we are dealing with machines, the thing that we're optimizing, machines that are fast at repetitive passing of data and the subsequent computation of it. Now, where they excel is that they've got perfect recall, but their intelligence is narrow, much like the hemoglobin cell who's focused on a specific task, except this machine is infinitely more capable in the task at which it is given. On the other hand, we have humans who are slow at repetitive passing, unlike the machine, as well as the computation of that, because our memory system, as we've seen, is very limited and unreliable. But we have general intelligence, which allows us to piece together disparate information in unique and creative ways. It's what allowed us to create the computer. So luckily, these two systems can bounce off each other and cater to each other's strengths. Now, I like to say that we know more than we understand in order to explain the previous point. What I mean is that if you had to explain every action involved in making a cup of coffee, you wouldn't be able to do so. Now, the reason for that, and the reason that I can tell you to make a cup of coffee, or I can tell you to go next door and you can complete that task without the low-level implementation details, is because that higher level area in which we excel is a world of whats and not hows. Because whats reduce the data transmitted to avoid using all our working memory. So where does functional programming fit into this model? We've slowly been introduced to a few ideas, the limitations of the human mind and some of the limitations of functional programming that are actually conducive to that. Let's go into them in a bit more detail. So we've already been introduced to the idea of a pure function in our introduction to lambda calculus, but let's look at it in a bit more detail and show how this simple idea is really conducive to good code that caters towards our shortcomings. So we saw an input of a pure function, or a pure function takes an input and it returns an output. It cannot reach outside of itself because remember, it was defined as a mathematical construct, and to be able to reach out to a place in memory just doesn't exist on a piece of paper. Now, what this does for us is it frees up cognitive processing power that would be needed to mentally represent and reason about those things which we cannot see. And by doing so, it focuses our limited attention. Remember, we've only got 7 bits of working memory, and to reserve some of those for trying to figure out what the implementation of a function is instead of being able to default to understanding that and focus on just what it's doing, it allows us to spend our time solving the problem instead of hunting down the information needed to solve it. On a human level, this optimization allows for repeated observation, which is that functions are lexically scoped to their environment. And remember, we spoke about behavioral adaptations. We spoke about the fact that it's a response to a repeated stimulus and that we try and optimize for it by reducing the resources required to perform that task. But the only way we can do that is if we consistently and reliably know that A will result in B. So if we see that functions are scoped to their lexical environments, we can confirm and strengthen this model, which means that we can devote more resources to attend to the function instead of reserving those resources to hunt for potential side effects. Let's look at this from a machine point of view. You see, if I'm a machine and I repeatedly observe that a given input always yields the same output, while if I was performing an expensive computation, I would be able to cache the results because I reliably know that for a given input, I will receive the same output. So we call this idea idempotency, the fact that for a given input, I will always receive the same output. If I wanted, I could draw up a truth table to represent my entire application and just have a lookup table to find specific values at specific times. This creates code that's incredibly modular. If my function doesn't touch anything outside of itself, it means I can swap it very easily because it's not tied too closely to anything. This means that all these very specialized mini functions, and we tie back to the original idea that we introduced this topic with, we can test the specific and specialized function, which is great for solid maintainable code. This serves to focus our code as well as our own attention, and this consistency brings about the benefits that we have discussed because it frees you from constantly needing to understand the differing nature of varying function implementations. Viewed from another light, as a result of the limitations, modularity comes naturally. You see, when a function is limited in this manner and when data flows through your application, as is required by functional programming, it creates this testable, modular, communicable code. Now, it still requires intentional design, but the limitations are more naturally conducive to the production of this code which caters for those areas where we lack. If pure functions and lambda calculus are the introduction to the world of functional programming, then category theory is where things get really interesting. Some people say that category theory is a great introduction to pure mathematics as it is an attempt to provide a framework for the analysis of mathematics. Now, the way it does this is it deals with the most abstract, and that shouldn't be confused with the most complex. The most abstract means most devoid of details. It is the act of trying to find the most useful commonalities that are applicable across a broad spectrum of possibilities. The result of these abstractions compose together in the form of objects and arrows, which is the most generic and abstract term we can give to potentially anything, is where we find ourselves and the base units, our primitives of this theory. I liken it to a design pattern, but with mathematically optimized relations. Now, we started off analyzing and looking at maths as a good starting point to mirror the world of coding. And I want to just go through that quickly again. Remember, it's an abstract logical representation of physical properties. It removes details because we're working with computationally limited systems, and it provides a framework of understanding, communication, and manipulation. Category theory can be very hard to learn because it's like learning a new language where the words don't map onto words you already know. So instead of just parrot learning or going through the difficult task of doubling up the information required to be able to communicate in some other form, you're asked to understand a concept without the language yet to do so. And once you've done so, then learn the language that maps onto this. And you kind of have to pick up the whole thing at once because everything is so interrelated. And this can be difficult. But if we go back to another slide earlier in our presentation, we remember that behaviors are adaptations to the environment. Our brain is good at taking repeated, consistent data and processing it efficiently. There was a point in time where you didn't know how to drive your car, but with repeated exposure and practice, you can now make a hot dog while you're riding 120 down the highway, changing the radio station. That's because your mind is so good at making neural optimizations. In fact, it's quite interesting to note that many functional programmers or people doing something where they've reached a level of mastery will speak about an intuition they feel for the subject matter at hand. They've done brain imaging scans where they've seen the networks involved for a novice and a master. And they've been able to track that the neural networks that are involved in the brain of a novice differ to the master, and the master's areas of engagement are actually the ones that are used for the regulation of our gastrointestinal system, which kind of lends some sort of credence to the idea that we truly do get an intuition, or rather a gut feeling for the things that we gain mastery of. Now, the task I set before myself today was quite a challenging one, and I did choose to approach it from quite an unconventional point of view, I think, and it was tricky compiling the information in a format that would be able to communicate effectively the ideas that I wish to share, but I hope that I have done so in an effective manner. And if, as my goal was not to convince you, but rather just to hopefully spark some sort of interest in a specific field of inquiry and to be able to illuminate some source of insight that may be useful to you in your day-to-day practice. And if you've made it this far through the talk, I'd just like to say thank you. I really appreciate the time that you've given me and allowing me to share this with you today. But most importantly, I'd like to thank the organizers of DevConf. I mean, unfortunately, we were not able to come together and do this thing in person, but it has still been such an incredible experience to be a part of this and to work towards it. And I would, yeah, like to express my heartfelt gratitude for the awesome work that everyone has put into this. For anyone who's interested in finding out more information about this, I've put together a few resources that you can check out. If you're just beginning and you'd like to know a bit more about category theory, I'd recommend watching a YouTube video. It's only about 40 minutes long by Eugenia Cheng called Category Theory in Life. She nicely illuminates the idea of how category theory gives our 2D representations of numbers a 3D representational structure that's positioned spatially and caters for our minds. She's also got a book on the art of logic, if I'm not mistaken, which is also a great read and gives an introduction to the idea of how maths allows us to think rationally and clearly about things. And I highly recommend it and think it would be great for all programmers out there. Secondly, for the lambda calculus side of things, a video series by Gabriel Lebec on lambda calculus is also available on YouTube. If you enjoy that and would like to go further, I could recommend the following books: An Introduction to Lambda Calculus, or An Introduction to Functional Programming through Lambda Calculus, guide you through the creation of your own Lisp-like language. The book's only about 100 pages long, but you go from the very basics of what that Lambda function is, much like what we did in the demo, but in a lot more depth. Um, Moving on to the category side of things, a good resource is by Brendan Fong and David Spivak. I like this one because there's also the MIT lecture series that accompanies this that they've posted on YouTube as well. And lastly, I think no list of category theory for programmers would be complete without Bartosz Mołewski. Um, Absolutely great series, tons of really in detail content by a man who is completely passionate about it. So, for those of you who are keen and would like to learn more, I recommend this. And also, interestingly, David Spivak, Brendan Fong, and Bartosz recently came together and produced a course which is also available for free on YouTube. So, you can go and check that out. But yeah, for me, that's all. I want to say thank you very much. And I guess we'll move over to questions and answers now if you have any. Thanks again for your time. Cheers.